Imagine you're building an app and your API is humming along nicely. A few requests per second, everything's smooth. But then something changes. Maybe your app goes viral. Maybe a bot discovers your endpoint. Maybe someone decides to hit your API 1,000 times a second. Your server starts struggling, response times spike, memory fills up, and then it crashes. Every single user gets an error. This is what happens when an API has no rate limiting. One bad actor, or even just a sudden spike in legitimate traffic, can bring down your entire system. And if you've ever seen this response, HTTP 429 too many requests, that's rate limiting in action. The server is saying, slow down, you're sending too many requests. But how does the server actually decide who gets through and who gets blocked? That's what we're going to explore today. The algorithms behind rate limiting and how they actually work under the hood. Rate limiting exists for three fundamental reasons. First, protection. Without rate limiting, your API is vulnerable to denial of service attacks. A malicious user can flood your server with requests, overwhelming it until it can't serve anyone. Rate limiting acts as a shield, capping how many requests any single source can make. Second, fairness. Imagine a shared API where one user sends 1,000,000 requests while everyone else gets nothing. That's not fair. Rate limiting ensures every user gets a reasonable share of your server's resources. No one gets to hog the bandwidth. Third, cost control. In cloud computing, every request costs money. CPU cycles, memory, bandwidth, they all add up. If someone starts making millions of requests, your cloud bill explodes. Rate limiting keeps your costs predictable. Think of rate limiting as a bouncer at a club. It doesn't matter how popular the club is, the bouncer controls the flow, making sure the venue doesn't get dangerously overcrowded. Let's start with the simplest rate limiting algorithm, the fixed window counter. Here's the idea. You divide time into fixed windows, say 1 minute each. For each window, you keep a counter. Every time a request comes in, you increment the counter. If the counter is below the limit, say 10 requests per minute, the request is allowed through. If the counter has already hit 10, the request is rejected. When the window expires, the counter resets to 0 and a fresh window begins. Simple. The implementation is incredibly straightforward. You need just two things: a counter and a timestamp for when the current window started. When a request arrives, check if you're still in the same window. If so, increment and compare. If the window has passed, reset the counter and start fresh. This approach is fast, uses almost no memory, and is easy to implement. It seems like the perfect solution, but there's a catch, and it's a big one. Here's the problem with fixed windows. Imagine your limit is 10 requests per minute. A user sends 0 requests for the first 59 seconds. Then, right at the end of the window, they fire off 10 requests. All 10 go through because the counter was at 0. Now the window resets, and immediately they send 10 more requests. These also go through because it's a brand new window with a fresh counter. So in a span of just 2 seconds, straddling the window boundary, 20 requests got through. That's double your intended limit. This is the boundary burst problem. The fixed window counter treats each window as completely independent. It has no memory of what happened at the end of the previous window. For some systems, this is fine. But if your limit exists to protect a resource that can only handle 10 requests per minute, allowing 20 in 2 seconds could be catastrophic. So how do we fix this? We need an approach that doesn't have these hard boundaries. What if instead of fixed boundaries, we used a sliding window, one that moves with time? The sliding window log works like this. Every time a request arrives, you record its timestamp in a log. To check the rate, you count how many entries in the log fall within the last 60 seconds. If that count is below the limit, the request is allowed. The window isn't anchored to any fixed boundary. It always looks back from right now. So that boundary burst we saw earlier becomes impossible. No matter when requests arrive, you're always counting within a true rolling window. But here's the trade-off. You need to store every single request timestamp. If your limit is 1,000 requests per minute, you might be storing 1,000 entries per user. For a system with millions of users, that memory adds up fast. You also need to clean up old entries that have fallen outside the window. So the sliding window log is accurate, but expensive. Can we get the accuracy without the memory cost? Here's a clever trick. The sliding window counter combines the low memory of fixed windows with most of the accuracy of the sliding log. You keep two counters, one for the current window and one for the previous window. When a request comes in, you calculate a weighted estimate. Take the previous window's count, multiply it by the fraction of that window still in our sliding view, and add the current window's count. For example, if we're 40% into the current window, 60% of the previous window is still relevant. So the estimate is previous count times 0.6 plus current count. If the previous window had 8 requests and the current window has 3, the estimated rate is 8 times 0.6 plus 3, which equals 7.8, still under our limit of 10. This uses barely more memory than the fixed window, just 2 counters instead of 1. And it eliminates most of the boundary burst problem. That's why many production systems use this approach. It's the sweet spot between simplicity and accuracy. Now let's look at a fundamentally different approach, the token bucket. This is probably the most widely used rate-limiting algorithm in production systems. Picture a bucket that holds tokens. The bucket has a maximum capacity, let's say 10 tokens. And tokens are added to the bucket at a constant rate, say 1 token per second. When a request arrives, it needs to take a token from the bucket. If there's a token available, the request goes through and 1 token is removed. If the bucket is empty, the request is rejected. Here's what makes this elegant. If no requests come in for a while, tokens accumulate up to the maximum capacity. Then, when a burst of requests arrives, they can all be served immediately using the saved tokens. So the token bucket naturally allows short bursts while enforcing a long-term average rate. The burst size is limited by the bucket capacity. The sustained rate is limited by the refill rate. The math is simple. When checking, calculate how many tokens have been added since the last check, add them up to the capacity, then try to consume one. That's it. The leaky bucket is the token bucket's close cousin, but with a different goal. While the token bucket allows bursts, the leaky bucket smooths them out. Imagine a bucket with a small hole at the bottom. Requests pour into the bucket from the top. And the bucket leaks, meaning it processes requests at a constant rate through that hole. If requests come in faster than the leak rate, they queue up inside the bucket. If the bucket fills up completely, new requests overflow and are dropped. The key insight is the output. No matter how bursty the input traffic is, the output is always smooth and constant. 10 requests might arrive in 1 second, but they'll be processed one at a time, evenly spaced. This is perfect when you need a smooth, predictable processing rate. Think of a print queue or a network interface that needs to send packets at a fixed rate. The trade-off is latency. Because requests wait in the queue, there's a delay between when a request arrives and when it's actually processed. The token bucket allows immediate processing if tokens are available. The leaky bucket always adds some delay. So which algorithm should you actually use? Let's compare them. The fixed window counter is the simplest. Minimal memory, fast lookups, but it suffers from the boundary burst problem. Best for rough rate limiting where precision isn't critical. The sliding window counter fixes most of the burst problem with barely any extra cost. It's a great default choice for most APIs. The token bucket is the most popular in production. It allows controlled bursts, which is usually what you want. Users can make a flurry of requests, then wait, then burst again. Amazon, Stripe, and most API gateways use token bucket variants. The leaky bucket produces the smoothest output. Use it when you need consistent, predictable processing rates. Nginx uses a leaky bucket for request rate limiting. For distributed systems, these algorithms are often backed by RIDIs. You store the counters or token counts in RIDIs so that rate limits work across multiple server instances. In practice, many systems combine approaches. A token bucket for per-user limits with a fixed window for global system protection. When you hit a rate limit, the server responds with HTTP 429, too many requests. But a well-designed API tells you much more than that. Look at the response headers. X-rate limit tells you your total allowed requests. X-rate limit remaining tells you how many you have left, and retry after tells you how many seconds to wait before trying again. As a developer, here's how to handle rate limiting gracefully. First, always check these headers. Don't wait for a 429 to find out you're close to the limit. Second, implement exponential backoff. When you get a 429, don't immediately retry. Wait 1 second, then 2, then 4. Give the server breathing room. Third, consider implementing client-side rate limiting. If you know the limit is 100 requests per minute, throttle yourself to 90. Stay under the limit proactively. The big takeaway from all of this: rate limiting isn't just about blocking requests. It's about shaping traffic. The right algorithm depends on what behavior you want to encourage. And now you know exactly how each one works under the hood.